Okay, so this is online lecture number 4, and the topic of today's online lecture is about making approximations. So in your homework set right now, you have problem 7.32 assigned, and that problem is challenging. The first challenging part of that problem is getting the kinetic energy correct. But the second challenging part of that problem is appropriately doing an approximation to simplify the Lagrangian. So by the end of this little online lecture, I'll give you some hints about how to do that problem correctly and exactly why it works the way it does and how you should understand doing approximations appropriately. Okay, so what we're talking about is approximations, and a sort of subtitle for the topic is something like this: sometimes first order approximations are not enough. And in particular, in problem 7.32 that you're doing on your homework, a first order approximation doesn't really make sense. So at this point in the lecture, many of you may not know what I mean by a first order approximation. So by the end of this, I hope you'll understand exactly what I mean by a first order approximation as opposed to a second order or a 0th order approximation, so that you can get a little more comfortable with how to use approximations appropriately. So let's, the basic idea is that if you have some variable, let's call it x for now, and you're given that x is somehow much less than 1 or much less than some other variable, then we know that if x is much less than 1, then x squared is something that's really, really small, much, much, much less than 1, and in fact is going to be much less than x. And likewise, x cubed is going to be much less than x squared. So if you're in this situation where x is a small number, then you need to realize this basic fact that the more powers of x there are, the smaller and smaller your result is getting. And therefore, if you're in the situation where x is much less than 1, then you can often neglect these terms that are of order x squared or x cubed. But by doing that neglecting, you're deciding how accurate do you want your approximation to be, right? So if you decide to throw out everything that is smaller than x squared, so let's throw out the x cubed, then you're basically deciding on what kind of accuracy you want to have in the problem. Okay, so let me make this a little more concrete. So I'm going to go through a few examples to make it clear, and then eventually I'll talk about how to handle the Lagrangian in problem 7.32. So example 1, let's consider this function, f of x equals sine of x. Now, I think even on exam 1, in various situations, I'm sure you've approximated sine x as approximately equal to x when x is small. This is the so-called small angle approximation, right? So I'm going to go through this process in a little more detail and make sure you're cognizant and aware of exactly how accurate your approximation is when you do a small angle approximation. So I'm also going to introduce these ideas about first order versus higher order approximations. Okay, but before I do that, first you need to remember that you can write the sine function as a series. That is, sine of x is equal to x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial plus da da da. So this pattern of increasing the exponent by 2 and dividing by the exponent factorial in this alternating sign here is how you can write down the sine function as a series. And once you see the sine function in this way, you can easily see that if x is small, much less than 1, then this x cubed is really small, x to the 5th even smaller, x to the 7th even smaller. So if you're going to approximate sine of x, then to first order, this is so a first order approximation of sine of x is okay, so I'm going to write down some categories here. So the approximation in first order is x. That is, first order, what it tells you is what is the power on x. So the power here is 1, the power here is 3, the power there is 5. So that here, first order refers to just the term that has x to the power 1. So this is the approximation. How accurate is it? How accurate is it? Well, it's got errors that are of order x cubed, right? So that is, the error is exactly equal to everything except for the x. But all of these things are much smaller than x cubed, so the error in this case is of order x cubed. So that's exactly how accurate your approximation is when you approximate sine x as being equal to x. Now, if you wanted to, say, go to a third order approximation of sine, which would be more accurate, then the approximation would be this. So sine x is approximately equal to this if you're going to be doing an approximation that's accurate to third order. And in this case, the error, or the inaccuracy of your approximation, is of order x to the 5th. Again, this x to the 7th and the x to the 9th that follows in this series are small compared to this x to the 5th. So if you want to know how accurate your approximation is here, it's x to the 5th. Okay? So let's do a slightly more complicated example. And then we'll get closer to what's happening in that problem 7.32. Okay, so example 2. Example 2 is going to be a sum of a sine x and a cosine x. Okay, so that's a function you might encounter. And now, again, I'm going to have you remember that we already wrote down what sine x looks like in a series. Remember that cosine x can also be written in a series. So cosine x is equal to 1, let's see, minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial plus da, da, da. So that's the series representation of cosine x. So if you put this together with the series expression for sine x, then we have that sine x plus cosine x is equal to 1 plus x minus x squared over 2 factorial minus x cubed over 3 factorial plus x to the 4th over 4 factorial plus x to the 5th over 5 factorial, and so on. Next sign is a minus sign. Okay, so this is a series representation of this sum, sine x plus cosine x. And once you get it into this form, you can start to see how you can do an approximation. So now let's do the same thing we did with the sine x. The approximation, we'll write down the approximate function. We'll write down the accuracy of this approximation. And we'll do this starting, in this case, at 0th order. Remember, so first order means that it goes like x to the first power. 0th order, oops, 0th order is x to the 0th power, in other words, of order 1. Second order, x squared, so on and so forth. So if we ask for the 0th order approximation of sine of x plus cosine of x, that is just keeping only this first term, 1. How accurate is it? Well, the accuracy, if again, we're in all these situations, we're talking about a situation where x is small compared to 1. So in this case, the accuracy is of order x, or the error is of order x, same thing. Okay, and if we were to go to first order, so this is the order of the approximation over here. First order is then keeping all the terms that are first order and lower. So 1 plus x in this case, and then the error will be of order x squared. So on and so forth. Second order approximation is 1 plus x minus x squared over 2. And here the error goes like x cubed. Okay, so oftentimes I just want to make one more point. Okay, I'll do that in the next example. Okay, so that is again giving you a slightly more complicated example of how you can do an approximation, and be careful about knowing what type of approximation, 0th order, first order, second order, and if you make such approximations, you should be able to identify how is the accuracy of your approximation getting better as you go to higher order. Okay, so let's go on and do a third example.